Let's see how your SQL knowledge can help you learn new skills. The first database system was the Integrated Data Store, or IDS, which was designed using a network model to encode relationships as a graph. It was a navigational database which required a program to walk through a file step by step using pointers, or chains as they were referred to in this presentation slide from 1962. Rather than telling a computer how to find your data by navigating from record to record with the network model, you could use Ted Codd's relational model to tell a computer what you want and let it figure out how to find it. Ted used to write example queries like this one on a blackboard, and then he'd show how to obtain the answer using relational thinking. If you had to use the network model, you would have to program each step of the process. Read an employee's record, then use the employee's manager to point to another record, and then compare the manager's salary to the employee's salary. In his 1970 paper, Codd described a blueprint for a query language based on first-order predicate calculus. His notation was a bit esoteric because he was a mathematician, not a programmer, but his specs were good enough to enable his colleagues to take the ball and run with it. Their first attempt to create a query language for Codd's model was named Square, and it was based on the notion of mapping a set of values into another set by means of a table. Columns were represented with subscripts, which were hard to type with a keyboard, and the syntax did not make queries very intuitive. So Square was like an original Hollywood movie, and what was needed was an even better movie sequel. SQL was literally the sequel to the Square language. It defined a more user-friendly alternative to the Square notation. And a backronym was formed from the letters in the word SQL to indicate that SQL was a query language structured using English keywords. The relational model still dominates the database world today, and SQL syntax hasn't changed much during the past 5 decades. The problem with the name SQL was that it was already trademarked by a British company for their sequence control unit, which was used to control and monitor the operations of industrial plants. Unfazed, the creators of the language said, "We can simply remove the vowels and still pronounce it SQL." They also dropped the word English from the backronym. At the same time Codd proposed the relational model, the first general-purpose, object-oriented programming language was being perfected. Simula 67 introduced many of the key concepts of object-oriented programming, like objects, classes, and subclasses with inheritance. To model a real-world object with a computer program, you need to decide what data will represent the object's traits and which activities the object can perform. For example, an employee object can have a salary attribute and an adjust salary method. When a program models business logic in an object-oriented way, a developer faces a mismatch between the app's object model and the database's relational model. Object-relational mapping frameworks bridge this gap. An ORM is a library that enables you to query and manipulate data from a relational database using an object-oriented program. So instead of using SQL, you interact directly with objects in your preferred programming language. An ORM abstracts away the database system, so you can migrate your database from, say, Oracle to Snowflake and still use the same object method calls to interact with the tables. The first ORM was named Object-Lens, and it was released in 1993 for a language based on Simula named Smalltalk. Object-Lens was included as part of the VisualWorks application development environment for Oracle and Sybase. Before we dive into ORMs, let's take a quick look at how a Python ORM would answer this query today. If you're not familiar with Python syntax, we use a session object to connect to a database system and call its query method. We use method chaining to make our programs easier to read by eliminating intermediate variables. Here, the query and filter methods will be used by the ORM to generate a select statement to pass to a database. An ORM is a data access layer that transfers data between an in-memory representation and a persistent data store. The ORM converts our object and its method calls into a SQL statement that will run on a database engine. The ORM I use is a Python package named SQL Alchemy, which was first introduced in 2005. They're making use of the second definition of the word alchemy, a process that transforms something in an impressive way, because SQL Alchemy transforms object-oriented code into SQL and then transforms SQL query results into Python objects. SQL Alchemy encourages higher-level thinking via a more Pythonic approach to database queries. The word Pythonic describes a coding style that leverages Python's unique features to produce code that is clear, concise, and maintainable. Using raw SQL statements is not Pythonic, but this may not be obvious until you see the results returned by a query. Our result is a simple list containing all the rows in the employee table. The first item in the list is a tuple containing data for each column in the table's first row. And the second item in a tuple is an integer for the salary amount. So a programmer has to know the index of each column and hope new columns are not inserted into the table later. SQL Alchemy enables you to use idiomatic Python code. The ORM returns a query object where each of the table's columns is an attribute of the object that you can access directly without needing to know its position in a row. There are many other reasons to use an ORM, including the prevention of the infamous SQL injection attack. SQL Alchemy automatically sanitizes user data for you before generating SQL statements. We'll take a look at two examples to see how similar the ORM syntax is to SQL. You will see that you can continue to think in SQL, but write in an object-oriented manner. We are computing the sum of sales for a subset of the customers. Most relational database systems can natively test for membership among a list of values by using the in reserved word. But not all databases come with a contains condition. To make its ORM language universal across all database types, SQL Alchemy will convert its methods into native operations, like here where contains was converted into a like clause. Once you get the hang of thinking in SQL while writing object-oriented code, using Spark or Databricks will be easier. In the PySpark code below, cust is a data frame object, and I'm calling its filter and select methods. The syntax for sum and contains are the same, and the membership conditions are very similar. Here's the last example, comparing SQL Alchemy to SQL. We're computing a count and giving it an alias that we can use in an order by clause to sort our results in descending order. Our call to the join method knows how to combine the media and tunes tables because there's only one foreign key between them, so it can create the on clause automatically. I hope you can see now that all your years of SQL coding can help you easily learn new skills.